In this video, we'll take a first look at the Prolog programming language and its basic constructs. So Prolog is a logic programming language. It may not become your main programming language. There's very few Prolog programmer jobs out there. It's not as efficient as, for example, C, and is not as widely used as perhaps Python or JavaScript. Still, Prolog does have some utility. It's useful for the sort of tasks where inference and knowledge representation take a central role. Prolog has an efficient syntax for modeling and interacting with rule-based systems. So you'll see it in some production-level systems, like expert systems, for example, where we essentially have a chain of inference leading from a set of known facts to some sort of strategy or like a diagnosis, if we were some sort of medical expert system. You also see it used a lot in natural language processing because language itself is a set of rules for representing information. For example, the International Space Station has a voice-based user interface that's written in Prolog. So Prolog does have some utility out in the real world, but the main reason we teach it in this course is because it will expand your mind about what programming languages can be. I've been teaching this course long enough that it started to seem quite normal to me, but I do recall seeing Prolog for the very first time and thinking it was a very bizarre language, or it almost seemed backwards in terms of the way it processes things. So logic programming in general, and Prolog as the characteristic logic programming language, it's based on predicate calculus from formal logic, which you might recall is a set of rules and notation that specify the meaning of unambiguous statements about some universe of discourse. So in logic programming, we're using the logical deduction as a general purpose model of computation. So logic programs, when they're written, are declarative rather than imperative. That is, the programmer's emphasis needs to be on the description of the system, the domain that we're trying to discuss, and a specification of goals, what we want to learn about that domain. But it's not, let's say, the programs do not direct themselves towards specifying the process, how to go from this specification of a system and these goals to some sort of answer to the questions that we've asked. Rather, a goal-driven process is managed by the interpreter itself. So the programmer's job in Prolog is to set up the universe and ask questions about that universe, and everything else is sort of left to the underlying Prolog system. So the Prolog interpreter needs to run in the context of a database of clauses. So to give an overview of logic programming, the first step is that we need to establish that database of declarative clauses. So this is also known as the Knowledgebase. It's also the program, or at least what corresponds to a program from other programming languages. So clauses are statements about the domain that are considered to be true. And there's two kinds of clauses in Prolog. There's facts and there's rules. So a fact, or all facts rather, are singular truths about the domain. Okay. These are things like Ottawa is cold or Ottawa is rainy. These are truths. These are things that we hold to be self-evident. Rules, on the other hand, these are considered to be relations between different symbols or entities in our domain. So these are used to infer one truth from another. If this is true, then we can also say that this other thing is true. Okay, so rule has the form P if Q1 and Q2 and Q3. So if all of these Q's in our conjunction are true, then we can infer P as well. Okay. So as an example in English, we could say something is wet if it is rainy, or we could say something is icy if it is cold and wet. Okay, so if something is cold and wet, then we know that it must also be icy. Okay, so we figure out what our domain is, and we try and codify some clauses, some statements about this domain, so to create this universe or this context for our interpreter. So that's the first step. The second step is then to query the database. So a query is a specification of a top-level goal for the Prolog interpreter. So a user can ask a bunch of different types of questions, like true-false questions about the domain, stuff like, is Ottawa icy? And if we had specified in our clauses some fact or rule that specified that it was, Prolog would say true. And if we didn't, Prolog would say false. Okay? So we can ask these true-false type questions, yes or no. We can also ask open-ended variable questions, like, what city is icy? And if Prolog can infer some answer from that, it might say Ottawa as an answer to that question. Okay, so a query instantiates this execution of the Prolog interpreter. It sets up the whole process. Kind of like how in Scheme we would say eval this expression. So eval was this request to process that expression, to do the computational steps from our inputs to our outputs. In Prolog, that process is started by constructing a query. Okay. So we've established a database of these declarative clauses, and then we asked a query, a question, about this database. And then the underlying Prolog system, the language implementation itself, will determine the process of answering those queries. So it has to work backwards from the goal, so the question that we provided, to find out if there's facts and rules that can imply that goal. Okay? This is a process called backward chaining. Now, in Prolog, the only truth that Prolog can rely on is things in the knowledge base itself. It doesn't have common sense or any sort of self-evident truth. It's only what we specify in this knowledge base or in the database of clauses. It's called the closed world assumption. From what we know to be true, we're asking, do these queries follow? Beyond that, Prolog will just say false, even if other things could prove it true. Those are outside of the scope of our program, so Prolog doesn't have any way of looking at them. Okay? So our query says, from what we know to be true, does this follow? And the interpreter will say, well, that goal is true if we can find something from the knowledge base that we know to be true that then implies this query or the truth of this query. Okay, so for example, if we asked, is Ottawa icy? Okay, well, we know Ottawa is icy if Ottawa is cold and wet, because we have a rule that something is icy if it's cold and wet. Okay, so now we know Ottawa is conditionally icy on these other two things. Now we need to prove, is it cold and is it wet? Well, we have this fact that Ottawa is in fact cold, so that's easy to do. And we can prove, or we can infer rather, that Ottawa is wet if we know that Ottawa is rainy. We also have a fact that Ottawa is rainy, so we know that it's wet, so then we know that because it's cold and it's wet, it must be icy. So it's this sort of backward chaining where we ask our query, is it icy? And it goes through the rules and facts in our knowledge base to figure out, can we say yes or no to that answer? Okay. So in this case, it would say yes, Ottawa is icy because our declarative clauses, our rules and facts, specify in a universe where that's true. Okay, so that's our intro. Let's move on now to running SWI Prolog. So yeah, for this course, we're going to be using the SWI variant of Prolog. There are other variants out there. There's a download link on the course website, and just on the main page there. The install should be straightforward, but again, if you ever have troubles, stop by the Discord or office hours, and we can get you set up. Generally speaking, you'll want a separate text editor. I'll be using Notepad++ or VS Code, depending on my mood of the specific day. So we'll have the Prolog interpreter downloaded, and we'll also need some sort of editor for our declarative clauses for our knowledge base. So when we open the SWI Prolog window, we get a window that looks like this. Let's bring these both up on the screen here. We have a cursor here blinking at what's known as the query prompt. So this is asking us to ask some information or pose some query to the Prolog interpreter. Now we haven't written a knowledge base yet, but we can still ask some simpler types of questions, like for example, does apple equal apple? Here we go. And that's true. And we can ask a similar question, does apple equal banana? And that's false. So we can see Prolog's still able to determine some things without a knowledge base being in place. And now you might think, well, what about that closed world assumption? We just said that Prolog only assumes things that are in the knowledge base to be true and everything else to be false. Now, the reason this isn't violating the closed world assumption here is because even though Prolog has no clue what these terms are, it has no idea what an apple or a banana is, it can tell that they are the same symbol or they're not the same symbol. Okay? And the answer will depend on Prolog's basic type, known as a term. So let's talk about Prolog's basic constructs here. So it's said in Prolog, perhaps a little bit strangely, that Prolog has a single data type. And that data type is known as the term. And then the term is divided into multiple kinds of terms, which might be a bit odd, but that is how the Prolog literature describes it. The general idea is that variables will unify, as it's called, we'll talk about that later, with any kind of information. So essentially they'll unify with any term. And then there's more specific rules for dealing with when terms are similar or dissimilar from one another. So the different kinds of terms. The main kinds of terms we'll deal with in this course are numbers, atoms, variables, and compound terms. Let's go through each of those. So numbers are numbers as you're used to them in most other languages. Now with Prolog, typically speaking, it's not a very math-centric language. The implementation here is usually for some sort of symbolic differentiation, not so much for some sort of mathematical calculations. Some compilers, including the SWI Prolog interpreter, will allow for real numbers, or just typically integers is what you'll normally see in Prolog. So we could ask something like, does 1 equal 1? And that's true. We could ask, is 3 less than 4? And that's true as well. Prolog does have a bit of arithmetic knowledge included as well. All right, so we have numbers. The next kind of term is what's known as an atom. An atom is very similar to what we learned in Scheme as the symbolic data type. So this is kind of the basic string of symbols representing items in our domain. So an atom is any symbols that start with a lowercase. So examples of atoms are the word John with lowercase j, book, owns, x, y, z, all of these, because they all start with a lowercase value, or sorry, lowercase letter. These correspond to atoms. They're considered essentially constant values, much again like the symbols in Scheme. They are just the characters that you see on the screen. That's all there is to them, right? Like with 3, it represents a quantity. It's not just the symbol. With atoms, they're basically just the symbols. Okay. SWI does include strings as well, but strings, because we have symbols in Prolog, are less common. Atoms typically get used instead. Okay, it does entirely depend on your objective, but for this course we'll stick to atoms. So the next type of term is the variable. So variables work very similar to variables in other languages with some differences as Prolog does. So if we want to define a variable, variables are any kind of term that starts with an uppercase letter. So examples of variables are things like person, item, name, x, y, z. And these are considered essentially placeholders. They're not the constant like John, book, and owns. These are more placeholders that person could be any person and item could be any item, whereas book is specifically that book and John is specifically that John. Okay. So obviously these things are case sensitive, unlike all the Scheme programming. You might have gotten used to not having to worry about the capitalization of your variables. Now, atoms start with lowercase, variables start with an uppercase, and messing that up is a very common source of errors, using variables with lowercase terms or atoms with uppercase, as you may find. Okay. So with variables, they essentially have an unspecified value. They're an empty placeholder, but they can be instantiated through what's known as unification, essentially making that variable equal to some other value. It's similar to assignment, but there are some differences. We'll talk about unification, I believe, in the next lecture. So a future video, at least. So in terms of other things that can be a variable, so all things that, all symbol combinations that start with an uppercase letter are considered variables, but there's a special case variable known as the underscore, which also counts as a variable. It has some special meaning, and we'll talk about that a little bit later. It's known essentially as the anonymous variable, or as I conveniently call it, the don't care variable. But again, we'll come back to that in time. All right. Now, the scope of a variable, once it is bound to some sort of value, is for a single statement or clause. So essentially till the end of a line, or till you find a full stop at the end of that line. But again, we'll talk about that once we see some examples on how variables work. Okay, on to the next type of term. So the next type of term is the compound term. So a compound term is essentially, it's a way of grouping terms into larger relations of these different symbols. So compound term starts with an atom, so it has to start with a lowercase letter, like some examples here, so like cold or owns. And these things are, their intent is to specify a relation in the domain. So something like cold Ottawa specifies that this thing in here has this relationship here. So this is a relation on a single object, just Ottawa is cold. We can have a relation between two objects, like John owns a book. Okay, so owns, John, and book. Now there's no pre-specified way of organizing these things. It's entirely on how the application designer or the implementation that you're creating wants to structure this knowledge. Okay, all Prolog is doing is sort of pattern matching and symbol combinations. So how we organize that John owns a book, we could have said owns book John, if that's how you prefer to think of it. You just have to be consistent through your entire application. Okay, so compound terms, they start with an atom, and then they're followed by a tuple of other terms, so 0 or more terms, so typically 1 or more. So that atom at the front has to be an atom. It can't be like a variable or anything, but the terms inside this tuple here can be anything. They can be numbers, they can be variables, they can be other atoms, they can even be other compound terms. So as an example, we could say a relationship called owns has one member called John and a second member that is some specific book, where that book itself is a relation between some title and some author, where an author is a relation between two names, a first and a last. Okay, so we can create these compound terms of nested compound terms, which even themselves have nested compound terms in them. So the rules for creating compound terms starts with an atom, again, lowercase symbol, and then a tuple of 0 or more terms, which can be any kind of term, including nested compound terms. Now, the number of arguments, or the number of terms inside this tuple, is what's known as the arity of that compound term. So the arity here. Oh, there it is. Arity. So if I say a relationship with arity 2, that would be something like owns here. It has 2 parameters. You want to think of it that way in the normal function call structure of this design from other languages. Okay, but I should emphasize here that this is not a function call. This does not specify that there's some function called owns that we're going to execute with the arguments John and book. That's not how Prolog works. All this is doing is saying there's a relationship called owns between John and book. This whole thing here could just be a statement of fact. Okay, it doesn't have to be related to anything else in the entire program. It could just be a simple statement of fact that John owns a book. Okay, so that's not a function call, even though it looks like one from other languages. It's just a way of structuring data, a little bit like a list, but with a bit more information. Okay, so those are the basic kinds of terms. We have numbers, atoms, variables, and compound terms. Let's continue on then with the rest of Prolog's basics. If you want to create comments, so you can have line end comments that start with the %sign, and you can have multi-line comments that look exactly like the familiar C or Java syntax. Okay, we'll see lots of those. That's for when you're creating the actual knowledge base, which we'll get to shortly. But before we can create a knowledge base, we have to figure out what goes into a knowledge base. So a knowledge base is built up of a bunch of clauses, and there's 2 different forms of clauses. So the first kind of clause is known as a fact. The next kind is called a rule, and they're very similar. A fact is essentially a statement about the universe that is always true, and a rule is a statement about the universe that is sometimes true, or true under certain conditions. Okay, so it's true if something else is true. So let's talk about facts first. So the syntax for a fact is just a compound term. So again, a tuple with some atom to start and 0 or more terms inside the brackets here. So again, typically 1 or more. It's weird to have a fact without any arguments, but it could happen depending on your application. So the syntax for a fact looks like this. We have the first part here, which is known as the functor, perhaps misleadingly because it is not a function. Again, it's just to match the syntax from other languages. So this is, again, specifies the relation that we're describing, and then the terms of that, which are typically the items of that relation. So some example facts, we might say, for example, Ottawa is cold. So it's a relation on a single item, Ottawa, having the domain-specific behavior or the domain-specific description of cold, whatever that means to Prolog. Okay. Other example facts, so we could say, for example, John owns a book. We've seen this one as well. It's just a statement of fact. It's a relation between 2 atoms, John and book, underneath this relationship header of owns. Okay. So it has to begin with this single atom. And then we have round bracket, a list of 0 or more terms, and then another round bracket, where each of those terms are separated by a comma. Spaces like that would be optional. Okay. So again, the functor for our fact needs to start with a lowercase letter because it has to be an atom. And if we want to specify that this thing is a fact, we end this whole compound term with a period or a full stop. That says this is the end of the fact. It's not conditional on anything else. It's just true. Okay. One thing to specify is that it is a syntax error to put a space in here. If you put a space between the functor and the terms, then Prolog doesn't see them as related, or may not see them as related depending on your implementation. So do not put spaces between the functor and the parentheses. Anywhere inside the parentheses is fine, right? If we have spaces between our arguments, that's okay, between our terms. But you can't put a space after the functor because then it separates it from the list of terms. All right, so as some examples, so we've seen the first couple. Here's another relationship on a single element. So the term John, we can say that in some domain that John is literate. Similarly, relation between John and Mary is that John likes Mary. Typically speaking, when you're reading these, it's the first one, and then the verb, and then the second or third one, depending on what you're dealing with. It's not always true. For example, a situation that doesn't follow that is add. We could say that if we add 2 and 2, we should get 4. Okay, so it's a relation between these three things, but where the first two are interpreted to be inputs and the last one is interpreted to be the output within the domain of that fact, right? We can tell from context that addition would take 2 and 2, join them together, and create 4. Prolog has no knowledge of that. It's just taking this information and joining it together. Okay, so these are all facts on constants, right? These are all using atoms as terms, or numbers as well, which are similar to symbols. But we could also have facts that involve variables, sort of universal facts, if you will. So for example, we could say John likes anyone by saying the first term in that relation between, or that likes relation is John, and the second term in that likes relation is unspecified. So uppercase X means that's a variable because it starts with an uppercase. And in that case, John likes anything that can fit into that space, which is literally any term. So John likes everything or anyone. Similarly, for multiplication, 0 multiplied by anything gives us 0, and we can capture that in this fact as well by saying 0 multiplied by whatever we put into this space equals 0. It doesn't matter what's unified with x, so long as it's a number, I suppose, but we would probably control that elsewhere in our knowledge base. This is just to show that we can create facts that don't necessarily have to be entirely constant, so this is universal type quantifiers. Okay. So we've seen facts. So facts are, again, just statements about the universe or about the domain of discourse that we hold to be unconditionally true. These will always be true about this universe. Okay. Rules, on the other hand, are very much like facts, but with some extra qualification. We say this is true under these conditions. Okay, we say if in order for John to like Mary, there needs to be something about Mary, so to speak. Okay, so the criteria for a rule, there's a bunch of criteria for a rule, so the syntax of a rule, looks generally like this. Notice the first part of this rule looks pretty similar to the first part of or the entire part rather, of a fact. Okay, or I guess the first part because we include not the full stop. So the head of a rule, as it's called, looks just like a fact, and it has the same sort of usage. It's saying this relation is true on these terms. However, because this is a rule, we're saying this relation is true on these terms if these following conditions are all held to be true. So this highlighted bit here, all these conditions, the body of our rule as it's called, is a conjunction of terms. Okay, so we have a head here, which looks like a compound term. We have what's called the neck operator because it joins the head and the body, so just colon dash. And then on the right-hand side, we have the body of that rule, and this is a conjunction of terms where if all of those things are true, that means the head of the rule is also held to be true. Okay? And as we'll see, we can have information in the head of this rule that needs to be verified in these conditions. So for example, we could have a variable that holds a person here and then determine that that person has some specific conditions. All right, what else about this syntax? So yeah, the body describes the goals to be satisfied or the conditions that need to be met in order for the head to be true. So the body is written as a comma-separated list of additional terms or clauses. So these things here could be requests to determine are additional rules also satisfied. So they look a lot like queries. We'll see some examples in just a second. The comma in the body essentially is a stand-in for the word and. If you want or, you can use a semicolon, but we'll see there's better ways or more conventional ways of using ors. Typically speaking, all rules in Prolog are written in what's known as horn clause form, which is a standard normal form that just says this is true if this conjunction of clauses holds true. So typically the body is always ands and the head is a single term. And if we want to do ors, then we can have additional rules for those as well. We'll see all that once we start creating knowledge bases though. Okay, so with all that in place, we have the head of our rule, some sort of neck operator, a list of all these conditions or a sequence of clauses that need to be true in order for that head to be considered true, and then the whole thing ends again with a period. Okay, so in terms of examples, we could create, we've seen this rule at least already, at least in our brief example at the top. So this rule here says x is icy if x is cold and x is wet. Okay, so if these two things hold to be true, then we will hold this to be true as well. Specifically, if these two things hold to be true about x, then we'll hold this to be true as well. Okay. We can have rules on no arguments, if you want to call it that. So rules with no terms here. So use an umbrella is true if the current weather is rainy. Okay. Typically speaking, though, the head of your rule will have some sort of variable just to make your rules more general purpose. Otherwise, you may as well create a fact. Right. So, for example, we could say x is a bird if x is an animal and x has feathers. We could say John likes everyone if that person likes Prolog. So kind of like our universal fact up here that John likes anyone. Well, now we have it a bit quantified. So we say, or qualified rather, John likes anyone if that anyone likes Prolog. So he only likes some of the people then. And then finally, a person will steal a thing if that person is a thief and that person likes that thing. Actually, that's an example from a larger example we'll see in just a minute. All right. So the example rules here assume the existence of other rules and facts as well, which is pretty common for rules. Generally speaking, the body of a rule is an additional query or an extended query, adds additional goals to our initial query, if you want to say that, where those then need to be satisfied, right? If our initial query was, is Ottawa icy? Well, instead of just knowing the truth of that, now we have two questions. Now we need to know, is Ottawa cold and is Ottawa wet? And those get satisfied in a similar way. We'll talk about the process of all of that. It's called resolution. It's a subject of a future lecture in a future video. But for now, just know that the body of a rule is typically comprised of other facts and other rules, or typically requests to determine are these things other facts or rules. Okay, a few other things to point out about rules. So I mentioned this, I believe, above when I was talking about compound terms, but once again, the number of parameters for a rule, so the number of terms in the head of the rule here, is again known as its arity. So this example here, icy has arity 1, whereas likes here has arity 2. Rules that have the same name but different arities are considered completely distinct by Prolog. There's no interplay between them, because if we have to ask, for example, does John like someone, or rather, does that someone like Prolog? We'll have to go finding a fact or rule in our knowledge base that matches exactly that pattern. We won't be able to find a single fact where X likes Prolog and some other part. I don't know. It was a bad example, but so different rules with the same name but different arities, they're considered separate because there's a different arity. Again, we'll talk about that once we get to unification in a subsequent video. There's a lot of me saying, we'll learn about this or this will make sense later in this introduction to Prolog. I realize that, but that is actually, I think, the best way to learn this stuff. Okay. Also about rules. If we have multiple rules that have the same name and the same arity, so if we have X is icy if it's cold and it's wet, and then we have another rule for icy that X is icy if the latitude is above 61 degrees, something like that. Okay. Then there's two different ways of proving that X is icy. Either it's cold and wet, or it's very far north. Okay. If either of those is true, then we can say that X is icy. So by having two rules with the same name and the same arity, let's say the same signature for the head, what we end up with is a disjunction for those rules. So we end up having X is icy if this, or X is icy if that other condition that I mentioned. Okay. All right, so then if we have a group of clauses that all have the same functor and arity, so a bunch of these disjunctions, if you will, these all jointly together specify a relation, and they're typically referred to in the literature as what's known as a predicate. Okay. Now, going through all of these terms, this introductory video throws a lot of new Prolog terms at you. If that gets confusing, or if there's ever a term you're not sure of, SWI does actually have this glossary, curated glossary here, hopefully opens, hooray. And it's a curated glossary of all sorts of Prolog words, like predicate and fact, and there's arity, the argument count. The number of arguments of a compound term is the arity. So if I ever use a term and you're not sure what that means, come back to this link here. So again, that link is inside the notes here, Prolog glossary for more details. All right. So we just saw facts and rules, which make up pretty much everything that Prolog does. Once we start creating knowledge bases, we'll see that the knowledge base is essentially just a bunch of facts and rules conglomerated together to sort of jointly specify the universe as a whole. And now a fact, really the only difference between a fact and a rule, is that a fact is essentially just a rule that is always true. So for example, I could write something like a fact like cold Ottawa. You wouldn't typically write facts here, I just don't have a knowledge base open, so I'm writing it here so you can see my text. So I could write a fact like this: Ottawa is cold. Now, because I'm writing this in the query, I'm actually asking the question, is Ottawa cold? So I'm not actually going to run this because Prolog doesn't know. So we could say this is a fact, but if we want, we could specify that as a rule in a very similar way, like this, right? Ottawa is cold is conditional on always being true. Okay, so you could say a fact is like a rule that's just always true. Okay, I think that's all I need to say about that. And that brings us nicely to knowledge bases. So I'm just going to delete this rule here because this isn't where rules go. This is where we enter queries. If we want to enter facts and rules, those need to be written into some sort of knowledge base. Now to construct a knowledge base, we just create a new file, and then we can enter all the facts and rules that we want. So let's do that. Let's go to our code folder. And in this folder, I'm just going to create a new text document, which will have the name demo.pl. Now, as a bit of a heads up, PL stands for Prolog here, and I have that associated on my system with SWI Prolog. But it's also associated with Perl Files. So if you already have an association for Perl Files and you want to have SWI Prolog work seamlessly, you can also use the extension .pro. But be sure to follow the naming conventions on assignments when you actually submit your files. And I'll always request .pl because it is, again, the standard for Prolog. Okay, so let's create a knowledge base. So we have this empty text file. Let's open it up with Notepad++. There we go. And let's just bring this across here, and we'll put that in the same spot. Okay, so if we want to create a knowledge base, we need to just enter a bunch of facts and rules that describe whatever domain we want to describe. So in this case, I'm just going to have some demonstration facts and rules. The first one is human is our relation, and Socrates is our term. So this says Socrates is a human, full stop. Great. And we can create another rule, or we can create a rule in addition, another clause. Mortal x if human x. So x is mortal if x is a human. Okay, so we have a fact and a rule constructing a very simple knowledge base here. Now if we save our code here, now all that's left is to bring that into the Prolog window so that we can access that file. Now there's a bunch of different ways of doing it. The simplest, if you already have the file, is to just double click the window here. Again, if it's associated with SWI, then it'll open up an SWI Prolog interpreter window, and it'll load in that knowledge base, or consult the knowledge base as it's called. However, since we already have Prolog open, I'll show you how to do that another way as well. So you go to File and then Consult, and this will bring you through a bunch of windows for finding things. So Consult. And if we go to CS/2020 1405, oh, not 1405, we are in 3007, Lectures, Chapter 8, into the code folder, demo.pl. So navigate down however many levels you have to get to your Prolog window, or your Prolog file, and open that up. If nothing is stated, that's a good thing. It'll say if there's any errors, but if it's successful, it just silently loads that in there. And then we're ready to start consulting this knowledge base. We're ready to start asking questions about this new domain that we've constructed. So once we've opened this up, there's other ways you can consult the knowledge base as well. There's also there's a Prolog command consult, and you can just say path to file in here. So as a string, sorry, path to file, and then you can consult the entire knowledge base that way. That's much harder than just doing it with the graphical interface through the file menu. So once we have this consulted in there, we can test by asking some questions about our Prolog query. Or sorry, about our Prolog knowledge base. So we've seen we have a fact and a rule. So we want to know, for example, is Socrates human? Human Socrates. Okay. And that is true. Now, the only reason that's true is because Prolog can find a fact from our knowledge base that asserts it to be true, right? If I ask human Andrew, myself, that's false. I am not a human because I'm just a disembodied voice that explains Prolog in YouTube videos. Socrates, on the other hand, we can see from our knowledge base is in fact a human because it says so right here. Okay. So we can ask all kinds of queries. We've already seen some other types of queries, like simple queries that ask, for example, arithmetic problems, like is 3 greater than 2.4? That's true just because of arithmetic. But generally speaking, we have a knowledge base. Prolog will check, does this follow from either a fact or a provable rule in our knowledge base? All right, so I can ask, is human Socrates? And that's true because there's a fact. I can similarly ask, is Socrates mortal? Socrates. All right. So to answer this question, Prolog has to then look at our knowledge base and see there's a rule here that says X is mortal if X is human. And then it needs to further prove, is X human? And we've already seen, if X in this case is Socrates, that X is human because Socrates is human because of this fact that we have on the previous line. So this is true, mortal X is true if human X, and human X is true because X is Socrates in this specific query. Okay, so I can ask, is Socrates mortal? And that comes up true. And similarly, mortal Andrew, false. I'll leave you to come up with your own backstory on that one. All right. So we can ask these very pointed questions that come up true or false of our Prolog knowledge base, but we can also ask more open-ended questions, things like mortal, and then leave a variable in here. Who is mortal? Now, in this case, the variable doesn't have to be the word who. The only thing that says that this is a variable, as opposed to just a constant that doesn't exist, is the fact that it starts with an uppercase W, which means this is an unbound term, and it's going to now bind with something that makes it true. So Prolog will work its way through the knowledge base. Again, we'll learn the process for that later on, to determine, is there some sort of value that I can stick into this variable that makes this statement true? And in fact, there is. If we say that who equals Socrates, that is, say if we put Socrates, the value Socrates, into the variable who, then this statement is true, as we saw on line 8 here, because Socrates is mortal. So this is true if that variable is Socrates. All right, so that brings us to the end of this video. We've covered a lot of the basics of Prolog. So we've seen what the single data type in Prolog is, the term, as well as the many kinds of terms that are out there. So we saw numbers, which are integers and real values. We saw atoms, which are these constants or these symbolic data types. We've seen variables, which look a lot like atoms but have uppercase letters. And then we've seen compound terms, much like our facts and parts of our rules as well. Okay. Then we also learned about clauses, and clauses come in two flavors, facts and rules, and they comprise a knowledge base. So this knowledge base is just a bunch of clauses that can jointly specify the universe. And then once we have that knowledge base in place, we can consult the knowledge base from a file as we've seen, or if you want, you can double click on it. We'll see other ways of getting to it later as well once we see some more examples. But once we've consulted that knowledge base, we can then query that knowledge base to get some more information. Like, is Socrates mortal? That's not specified anywhere in our knowledge base, but it can be inferred based on the facts and rules that are in so that we know that that's true. All right. That's the end of this video. In the next video, we'll get into some introductory Prolog examples, and I will see you in the next video.